on this concept called Monte Carlo tree search. My name is Eli, this is Huan. So let's begin. Today's agenda, first we'll introduce to you guys the idea of game trees, what they are. Number two, why use Monte Carlo tree search? Number three, what is Monte Carlo tree search? And number four, how abbreviated MCTS is applied in the real world. Okay. So games and complexity, yeah, it is a very big topic. So I'm sure all of you have played games before, right? So you have to actually pit yourself against maybe the computer, like the AI. Yeah. If you all can just go here, right? This is a very simple example. You can actually just go to Google and search tic-tac-toe. And then you can play against Google's tic-tac-toe board. So you can actually do this. You set the difficulty to impossible. And then you realize, right, that every time you try and play the AI, you can never win. No matter how many times you try. Yeah? So how does this thing work? Okay? It's actually with an algorithm behind where it uses the algorithm to evaluate each and every possible game state in a given game tree. Okay? So from here, I know it's a bit hard to see, but bear with me. So you start from here with an empty board. Okay? How many possible moves are there? For the next player, it's just 9 for tic-tac-toe, right? 9 possible positions. But here you just show 2, if not the entire chart will be so unreadable. So then you go blah blah all the way to the end, where you end up with ending game states, yeah, where one player wins, either a win, a loss, or a draw. So this is a bit hard, but let's just condense that down. I'll be showing you guys how it's actually evaluated. Okay, so it's actually using this algorithm called Minimax, yeah. So it's just a simple algorithm to evaluate turn-based games, yeah, or it could be applied elsewhere, I think. So you will search the game tree for the best possible move, okay, the next best possible move. So for games like tic-tac-toe, right, where this idea of branching factor, so you go back here, right, it will actually branch out 9 times, right? Okay, but for games like chess, for Go, for example, okay, the branching factor is actually extremely high. So you might actually want to do a partial search rather than go all the way to the end. So the evaluation function to score the game tree positions is actually what gives each game state its score. So let's just look at a diagrammatic playthrough okay, to better understand it. So here we will have 2 players, okay, the white player who is the AI and black the player. Okay, the objective, right, of Minimax is from its name is to max. For the white player, he wants to maximize his score. For the black player, he wants to minimize the score. So let's take a look at this. So we have the white player, the black player chooses the next step, the white player chooses the next one, and then black chooses the next one, right? So over here, this lowest row, I'm sorry for the bad contrast, okay, it's actually the end game states, yeah? So let's say you have -1 and 3. Like you evaluate that, you go all the way down, you evaluate that game state to have these scores, right? So because here, the white player wants to make a move, you actually choose the max out of these 2. Okay? And then you do the same for here. If my scores are 5 and 1, so given that I'm the white player, which one will I choose? 5, right? Okay, so then now it comes to the black player's turn, yeah? So which one will I choose? Because the black player wants to minimize the score, then he'll choose 3. Yeah, so it's simple like that. I do the same for the right side of the tree. And then because it's the white player's turn, I'll choose the max of these 2. So I'll choose 3. And then this is the path that I shall take. Yeah? So the minimax function looks like this. It's recursive. So minimax, you take in position, depth, and the maximizing player. In that you need to keep track of whose turn it is. Is it the white player's turn or the black player's turn? So if depth equals to 0 or the game is over, this is pseudocode, of course. Yeah, you will just return a static evaluation, okay, of that particular position. So this the base cases, right, the bottommost row. Okay, so if you are the maximizing player, then you will set the max evaluation to -infinity because you want to find the maximum score. Yeah, so for each child of position here, we have a simplified version, like just have 2, right? So you just call it recursively all the way down, and then at the end you just return the max evaluation. Okay, if you are the maximizing player. If on the other hand you are the minimizing player, you will just, for each possible next move, you will find the minimum. Okay, So this is pretty important. Yeah. How do you actually get the evaluation of the game state? Okay, this for tic-tac-toe, I think it's probably like number of paths to win or something like that. I don't know. So we put some black box here, some eval logics. Okay, then you just return the score. So the branching factor that I mentioned just now, okay, is actually visualized here. For the tic-tac-toe, right, it's actually quite straightforward. You only have 9 possible places. It's static also. Once a player puts an X or a player puts a O, right, you can never change that, right? But for games like chess, Go, etc., the pieces can constantly move around. So the branching factor is pretty enormous, yeah. So just to have an example, this is known as Shannon's number, I think. So the number of possible unique games that you can play with chess is actually estimated 10 to the power of 120. But atoms in the observable universe is just 10 to 80. So you can imagine how complicated chess is. So given that we have extremely complex games like chess and Go and so on, right? If we use the Minimax algorithm, yeah, it won't work because of the enormous branching factor. So how then do we evaluate game states, right? How do we actually get to how do we evaluate, oh yeah, this is a possible, a good game state that we want, yeah? So Yuan will be sharing with you guys on how Monte Carlo tree search will be used for this.
Okay, so we're here to talk about Monte Carlo tree search, not Minimax. This is the main body of what we're going to talk about today. So basically, as Eli mentioned earlier, right, some games are not possible to be evaluated using Minimax, like chess, because there's just so many possible branches. So how do we know which is the best next move? So in this case here, right, you can ignore the words for now. Just look at this one particular tree. It's just a tree that like we learned in class. So the value on the left, right, is the number of wins, and the value on the right is the number of visits. Okay, so what do I mean by wins and visits? So what's happening here is that the root node, you can take it as the initial game state or just any game state, okay? So let's say maybe the initial game state is an empty board, and let's say maybe tic-tac-toe, right? So we have 9 possible moves. So in this tree, let's just say that we have 3 possible moves. So for each possible move, right, what I will do is that I will simulate some game. The computer will simulate a game, and then it will determine based on that simulation whether from that move, right, can I win or not. Okay, so I think it's a very abstract. So let me just go down to the pseudocode. Okay, so so given the tree, right, you select the best node to simulate a game based on what we call the upper confidence bound for trees, the UCT. So basically, UCT, you can think of it as whether you will want to choose a node to simulate, or choose a node to visit, or you want to choose a node that you never visit before. Okay, later go example. Okay, I know it's a bit confusing. Okay, then after that, right, it's expansion. So like before, right, so given this, let's say I hit this, whoops. So let's say I hit this node 3, 3, right? Oh, whoops. Okay. Whether do I need to expand the node to go to the so-called the next play, right? And then simulation, the computer will play itself, usually through random moves to decide whether the game can be won or not. And then backpropagation is it will tally out the results, and then it will send those results up the tree to the root. Okay, very confusing. So let's go to the example. Okay, so I have an initial game state here. Okay, so because the root node is technically like a leaf node, right? So I need to expand the tree. So I will expand the tree with the possible moves from that game state, right? So now I will simulate. I will select first. So I select the leftmost node because I have never visited the node before. I don't know whether I should simulate it or not. So I just go and simulate it. So I simulate random moves. I say that, okay, I can win from this game state. So I will say that I visited the node once and I won once. Then I will do the other node because I never visited it before. So let's say I lost. So I never win, so 0, but I visited it once. So what's happening here is that it will propagate the results back to the root node. So now there's 1 win and a total of 2 visits. So and then okay, so let's say now I choose. Okay, I need to choose between 1-1 or 0-1. I will choose 1-1 because because I won from that move, right? So I will choose 1-1. So 1-1 is a leaf node, so I will expand it. Let's say there's only one more move, so I will expand it. I win. I will choose 1-1. I'll set 1-1, and then I'll propagate the 1-1 result up to the parent node 2-2, and then propagate up again to the root node 3-4. So given this initial game state of this 3-4, right, I know that based on my probability testing, right, that the best move to do would be to take this particular branch. Okay, and the way it differs from Minimax is that I don't create all the possible branches. So if you look at the MCTS for Go, right, this is it's like just 3 moves, and you can see that there's like a crazy amount of branches. But this is still less than what Minimax will have to go through to get all the possible moves. Okay, so why use MCTS? It's not domain specific. You do not need to know how to play the game. You only need to know how to win it. Unlike in Minimax, where you need to know how to play the game to get all the different states. Okay, also similarly, there's no need for an evaluation function. Once again, you just need to know whether you win or you lose. You don't need to care about evaluating a certain game state. And finally, like what I mentioned earlier, it will minimize the scope, the search scope, because only nodes with the highest UCT are simulated, not every single possible game state. And some advantages, examples. So Alphago, as we know, Alphago uses both MCTS as well as deep learning to beat the world champion, and also even in games like AI, where there's like a lot of different moves, right? You can use MCTS to simulate what is the best move the AI should take. So, yeah, thank you. Any questions? I don't know. Yeah. Oh.
Can you explain more on the part where is the node and the root?
Okay. So this one?
Yeah. So we'll choose the left because it's success.
Okay. Okay. I wanted to explain, but I think I ran short of time. Okay, basically, yeah. So basically, how you select a node, right? Okay, let's say you are in a room. There's a lot of jackpot machines. Okay, and all of them have a different probability of hitting a good result. But then you don't know which one is the good one, right? So logically, you go and test all of them because you don't know what, right? So in this case, right, because you can think of empty as you never visited, you never tried a machine before. So if you never tried before, obviously you want to try it, because you don't know what kind of result it will give you. So let's say I try out my leftmost machine, and I realized that, okay, I tested it once, and I got a good result one time. Okay? And then now I test the right machine, because I never tested before, and then it didn't give me a good result. So at this point of time, will you choose the one that gave you a better result, or the one that gave you a worse result? The one is the better one, right? So that's why I will play the machine again to find out whether it gives me a good result or not. Yeah.
That's 1, 2, 3 times, right? The play.
Yeah, as in, okay, jackpot, I know you play once, but as in, this one is like a board game, so like different moves. Yeah. So each level is a different move.
Okay.
Yeah.
One important point I think we didn't address is when do you actually stop. Because you can actually run the simulation multiple times, like for however many times. But once again, that one is based on a...
Yeah, it's as in you can run this simulation, right, based on a number of iterations or like a certain period of time.
Or online examples say when you get bored.
Yeah,
or you run
there's
out
like
of
some time, there's some time to...
So it's a heuristic ultimately.
Yeah. Any more questions? No? Okay, thank you.
How do you generalize to more than 2 players?
Sorry?
So can you have more than 2 players? So far you're talking about AlphaGo and so on.
Yeah,
so
as
it's against another guy.
we didn't see any examples online of games that apply to more than 2 players.
So I think at the end of the day, it depends on how a win is generated. Because ultimately what we care about is what is the definition of a win. Because how MCTS works is you don't have to know how to evaluate a particular game state, you just need to know when you win. Yeah, so you just simulate until you win, and then you know that we backpropagate, so you know that the path has taken the score. Yeah. Okay. It sounds like you know the answer, bro.
Alright, thank you.
Okay.